Okay, in this video we're going to take a look at an introduction into related rates. And in related rates we're going to use implicit differentiation, and each problem is going to involve a different formula that we're going to take the derivative of, and most of the time we're taking the derivative with respect to time. So no matter what our variable is, it's going to be with respect to time. So for instance, if we're taking the derivative of the volume, the derivative of that would be dV for volume over dt for time, usually in seconds or minutes or whatever the case may be. So the first thing we're going to have to look at is coming up with a strategy to solve these problems. The first thing is to read through the problem and get an understanding of what it is that's taking place, and then start writing down potential equations and listing what's been given to us and labeling it properly. So let's just take a look at this and see if we can come up with a little strategy here. First thing is this balloon is being filled up with a constant rate of 5 pi cubic centimeters per second. So you'll get pretty good at recognizing this stuff with a little bit of practice. So this constant rate is in cubic centimeters, so that's a volume measurement, and it's being inflated at a constant rate. So that's going to be our rate, is going to be our dV with respect to time, right? So it's not just 5 cubic centimeters, it's 5 cubic centimeters per second. So we'll go ahead and list that known quantity right here. And we'll just leave the units off, but maybe on this first example we'll try to maintain them for a little bit. And what else do we have here? It says, what is the rate at which the radius is changing? So that's a question, and it's asking us, what is the rate? So the rate at which the radius is changing, and it's all with respect to time. So ultimately what we're looking for is dr dt. So maybe over in the corner somewhere, just write down what it is you're looking for. So we have to come up with a formula that deals with volume that has radius in it. So this is maybe a formula that you don't have memorized, but no doubt you've used it before, perhaps in geometry or something. But the volume formula that we're interested in is of a sphere, and it's 4/3 pi r cubed, pi r to the third power. So we notice here that this problem's really not too bad because we only have two variables. Don't make that classic mistake of thinking that pi is a variable. It is in fact a constant. Of course you know that. So what we're going to do is we're just going to start taking the derivative. And if we take the derivative, on the left side all we have is volume. So the derivative of that is going to be dV dt. Okay, and just to recall what we just talked about, we know what dV dt is, right? We kind of identified that out of the problem. That was given to us. So that's a good thing. And remember, 4/3 is certainly a constant. Pi is certainly a constant. So the derivative of this is going to be with respect to time of the radius. So the derivative of this is 4/3 pi. And now we take the derivative, 3r squared. And remember, this is implicit differentiation, so every time you take the derivative, it's with respect to time. And so it's going to be dr dt. And this is good right here because this is what we're looking to solve for, right? Dr dt. So now all we have to do is plug in our known values, and then we're going to solve for dr dt. So it just becomes a little algebra problem. And we notice that in this problem we're only interested in the radius when it's equal to 112 centimeters. So it's kind of a unfortunately large number. We're going to have to use a calculator for that. But let's plug in our knowns. dV dt is the only thing given, and it's given to us at 5 pi centimeters cubed per second. And we can clean up our derivative a little bit. If we multiply 4/3 times 3, we get 12 over 3, which is just 4 pi. And we're only interested in 112 squared. That's our radius that we're looking at. And then I'll change colors here, kind of keep it straight here. We have our dr dt, which is what we're trying to solve for. Okay, so all we're going to do is, well, I didn't put my units in there, did I, for my radius, but it's going to be in centimeters. See if I can erase this without doing too much damage. This quantity was squared, and we're trying to find dr dt. So look what happens. If we solve for dr dt, we're going to have to do what? We're going to have to divide this entire quantity over here. This quantity right here is going to be divided out. So doing that, we'll have 5 pi centimeters cubed per second. So the second's going to be in the denominator. This might get a little messy, but I think it's worth doing it at least once. And then we're dividing it by 4 pi. And 112 centimeters squared. Let me erase this because it's going to get quite big here. Put our seconds over here at the end. We're dividing it by 112 centimeters, and all that's squared. And we notice a couple of things that cancel right away. Pi cancels out with pi, and so we're left with ultimately 5 cubic centimeters on top. And then using the calculator, we can punch up 4 times 112. So let me do that over here. I got a little calculator in the background. You can't see it. So it's 4 times 112 squared gives me 50,176. Okay. Apologize about the size of these numbers here. 50,176. What I really wanted to do is just emphasize my units. So I have what? Centimeters squared, because I squared 112 centimeters. And then I still have my seconds down here on the bottom. So before we punch up this final answer, let's just take a look at our units and what cancels here. So we have centimeters squared, which cancels, and it's going to cancel it's going to cancel centimeters squared and leave me with just centimeters. So my only units that I have left are centimeters per second, which is what the rate of the radius would be, right? Because radius is a single dimension unit there. It's not squared, it's just to the first power. So I'll spare you the details, but ultimately, and what do we solve for? We solve for dr dt, right? So dr dt, I think I did it in purple. Dr dt, dr dt. So the radius, with respect to time, is changing at a rate of, and once again I do apologize for this number, I got 9.965 times 10 to the negative 5 centimeters per second. Okay, so at this point, when the radius is this big, the balloon's radius is not changing a whole lot. So hopefully you can follow along with this video, and we'll try another example.